So good morning again. Let me make a brief recap of where we are. Mm, we are discussing, of course, climate change adaptation, and therefore we had a couple of lectures on risk estimation. Risk estimation, as you may remember, entails probability, some concepts of probability. I know that you know, probability is something that usually students don't like. I hope that this year I decided to take a different approach, as I mentioned to you. So I hope that this different approach may help you to get better confidence with it. I am sure that you had probability in your background before, but still, when I get the comments of the students, I see that this topic is still something that may result a little bit critical for you. So if you, again, if you have any suggestion about it, that's fine. But of course, we are talking into the context of climate change adaptation. So while I was introducing probability and risk estimation, I decided also to make a kind of narrative break in order to start understanding what are the risks induced by climate change, which we have to adapt to. I started from water resources, but we will have other focuses on other risks. I started with water resources. I told you the motivation because several impacts of climate change are passing through water. Basically, water is the mediator between the climate change and the human society. Water is like a channel of communication between humans and the environment. Of course, it's not only water, but water is delivering most of our relationship with the environment through, for instance, of course, drinking water, through water for irrigation, through energy production, through also risks which are related to lack of water, droughts, and excess of water, floods. And also water is a key driver of landscape instability, landslides. So you understand that it's something that is indeed important in establishing our relationship with climate and therefore with climate change and the environment in general. So this is why now we are focusing on water resources in order to understand what is their distribution, why they are important, where they are lacking, where we have flood risk, etc. This is an active topic of research because the impact of climate change on water resources is still presenting several unknowns, and therefore, as I said, this is still an active topic of research. I am making an effort to provide you information with two purposes. First of all, to provide up-to-date information, because we need the most recent information. And also we need to stay up to date. The information is continuously delivering innovation, and therefore we need to be fully informed about this innovation. This is the first purpose, so to be up to date. The second purpose is to give you information at the technical level, and this is in itself a big innovation, because actually we are still making a lot of research on how to take into account climate change when developing technical applications, when passing to practice. Technical applications are not only engineering, it's also policy making, it's also economic strategies, it's also energy production. So as I said, it's not only engineering, and therefore it is what we need actually in order to make actions, in order to adapt. Okay, so let me, after this introduction, let me share the screen. Here we are, and in particular my web page. Here we are. Good. Okay, climate change adaptation. And where are we? First of all, I changed the order of the links in order to reflect the order we used them, okay, during the lectures. So we are focusing on these two links, risk-based adaptation design and sustainable management of water resources. So I propose that I move forward with the sustainable management of water resources. Let me download the PowerPoint. As you know, there is the PowerPoint at the end of the story. Okay. At the end of the lecture, there is the PowerPoint. And here it is. Okay, good. Perfect. So we got here. No, sorry. I'm okay. Yeah. I have to go to move forward. Just 1 second. Okay, here we are. I got lost. Just 1 second. I want to make sure that I got sustainable management of water resources. Yes, okay, it's correct. So here we are. Good. Okay, this is, but we got not just here, we got here. Okay, classification of climate. Climate is relevant to determine the distribution of water resources. This is why I'm providing this classification. Before classifying climate, we saw the distribution of rainfall, spatial distribution of rainfall. We highlighted that rainfall is concentrated over the equator. And over the equator, we have the highest amount of rainfall. So what is this highest amount? You see that in terms of millimeters per day, if you see the color scale after the in the bottom of the picture, if you see the color scale, you see that it's varying from 0 white to about a little bit more than 6 millimeters per day. So 6 millimeters per day means 400 times 6. It means about 2,500 of annual rainfall, where you see the dark blue colors. So 2,400 millimeters, so 2.5 meters of rainfall in a year is indeed order of magnitude. It's more than order of magnitude. Is a precise indication, quite precise indication of the max amount of rainfall that on average you may expect in the most rainy regions of the world. So around the equator, you may expect about 2.5 meters of rainfall every year. It means that if you put a tank outside and you exclude evaporation, and therefore the tank is continuously filling as new rainfall comes, at the end of the year, if you put the tank outside on January 1st and you go there at the end of the year, on average in these equatorial regions, you find 2.5 meters of water. And this order of magnitude is important. If you talk about climate, and if you talk about, in particular, about water resources, it's extremely important that you have an idea of the order of magnitude, and in particular, the order of magnitude of annual rainfall. Annual rainfall is an important indicator of water resources availability. Of course, it is an aggregated indicator. It doesn't tell you how rainfall is distributed over the months, over the seasons, but still it's an important indicator. Where you see the dark blue here on the globe, therein they don't have water problems, substantial water problems related to availability. Maybe that they have other problems related to floods, related to water quality, but in terms of quantity and in terms of availability, they don't have huge problems where you see the dark blue. Again, 2.5 meters. What is an indication of average rainfall over Italy? It depends, because if you see Italy here, you see that the distribution of rainfall varies from light blue to green. So green is 2 millimeters per day, which means about 700 millimeters per year. light blue is maybe something like 3 millimeters per day, which is about 1 meter of rainfall per year. Indeed, in Italy, in the north of Italy, the indication of the amount of rainfall is precisely something like 1 meter per year. In the most rainy regions of Italy, which are in the northeast, and in particular the Friuli region, here we have the highest rainfall, and there are locations which experience about 2.5 meters per year, indeed, comparable to the rain that you get in the most rainy regions of the world. In the south of Italy, you get, of course, less rainfall. Italy is very elongated in the north-south direction. It's about 1,000 kilometers. In the south of Italy, there are regions with about 500 millimeters per year of rainfall, the arid regions of Italy. In Bologna, we have an average rainfall, which is nowadays about 700 millimeters, to give you an indication. Okay, these orders of magnitude are important, as I said, if you talk about climate. Okay, and then here there is the climate classification. It's not necessary that you learn it. It's just necessary that you know that today we have this climate classification proposed by Köppen, which is the most used in order to have information about the distribution of climate over the world. And there are more details in my web pages. I'm not going into the details here because, as I said, this is not something that you need to know in deep detail, but just be aware that if it happens to you to talk about climate and the climate of a given region, your reference is, for now, it's the Köppen climate classification. It's being evolved recently. It has been evolved with some more sub-classifications. So, of course, you have to stay up to date, as I said, but there is also the link in my webpage to the Wikipedia page of the Köppen climate classification, where you can get the most updated information. Now, the distribution of water resources is comparable to the distribution of rainfall. So here you see that the colors are proportional, are related to the amount of total renewable water resources in per inhabitant in 2014. So these are renewable water resources per inhabitant in 2014, cubic meters per year. Renewable means that they can be renewed, so they are water resources which are available in water bodies that are replenished, like rivers, lakes, like groundwater, if it's replenished. And it is per capita, this distribution. Actually, as I said, it doesn't give you any additional information, this figure, because the colors here are directly related to the colors of rainfall, which we saw a couple of slides ago. What is very interesting in this picture is the source of the data, which is the database called Aquastat of FAO. This is extremely interesting if you need data related to water and several type of data. This database, it's a useful reference. So let's have a look on the web at this database, because I want that you know that it's very easy to find information on it, and this database is frequently used for making research, and it may be a useful reference for you, for your thesis, for whatever you want to do. Or if you want, for instance, to deliver a presentation during this course on the status of water resources in your country, you can find useful information here. So let's go to a web page, to a Google page, and let's find the Aquastat database. It's a bit of time that I didn't since I lastly accessed it. So first of all, let's click on the main link here, and let's see if how it looks, the introductory page. So the FAO is the Food and Agriculture Organization of the United Nations, and you see that there is several information that accompanies this web page. And let's focus on our database. Okay, so databases, there is also geospatial information. There is also a section on data analysis. Let's look on databases first. So here there is the menu where you can find country statistics, dams, institutions, etc. Let's click on country statistics, and let's see the database again. You have to get some experience to navigate these websites. Keep in mind that getting data from the web, as I said already, it's not easy. It is not easy, and it is something that you need some training, and because there is a lot of information available, and they use their own format, etc., in order to present the data. And this is why some training, some proper training is essential. So water resources, let's click here, and let's see, here you see that you can select the country and the year. And the water resources, let's look at, for instance, internal or total renewable water resources. Let's see if there is a variable, some variables appearing here. So total renewable groundwater, total renewable surface water, total renewable water resources. Let's click on total renewable water resources per capita to see if we can get the data that we were looking at just some time ago on the presentation. So let me see how show data. Let's please note, okay, let's remove this note and let's click on show data. Okay, there is also a download that is possible, but let's see if we can get the data. We have to wait a little bit for the generation of the map, I think. Let's see. I hope that it's not too long. So download, let me try to click on download. Okay, it's an Excel, and if you open it, there is nothing. Okay, let's go back. Sorry. Okay, I made a mistake. I closed the window. Just let me go back again. Aquastat. I go faster this time. Okay. Databases. Okay. Databases, country statistics, database. Let's see. Variable group. Okay. Water resources. Let's wait for the subgroup. And let's, okay, total renewable water resources. There is also precipitation, which is interesting as well. And the total renewable water resources per capita, show data. Okay. 1 second, show data. Let's see if we can get. I think it needs some time. So let me just go back to the presentation, and then we come back here later to see if something appeared. And in any case, I wanted to give you some demonstration, some training, so that you have also the opportunity to check yourself, to navigate yourself if you want to see some data. Let me just check here, navigate. Okay, let me see. I think probably I should select whole here, the year. Let's select an year, 2019. I think there was another selection in all countries. I missed these selections. Okay, I missed these selections, and let's see if now we can get something more. Okay, this is a table, we can download the data, and there is also the opportunity somewhere to get the map. You see that here there is a table for all countries with the total renewable water resources per capita. And so you can find your country if you're interested in it. And I am sure that there is the opportunity to get a map also if you navigate the website. And I don't want to take your time now, but just have a look if you are interested, okay? Perfect. So let's go back to our presentation here. Okay, and here you see some other maps. This is the proportion of renewable water resources withdrawn, and it is also providing this information. It is providing this information in terms of an indicator which is called the Millennium Development Goal Water Indicator, which is also called with the acronym MDG. So this indicator is it's interesting because it highlights where are the regions in the world where most of the renewable water resources is used. Here in dark colors, and in particular with the red colors and the brown colors, you see the critical countries. Because if you look at the percentages, the brown color corresponds to more than 75% of renewable water resources that are used, which means that there is not much margin. And the reason is that, you know, the distribution of water resources, as I said, it's uneven. And there are some regions of the world where most of the water resources are used, which means that you don't have room for increasing, you have limited room for increasing the use of water resources. Remember that the use of water resources is an indicator of the welfare and the wealth of people. Yeah, where you have more water available, it means that you have more opportunities for developing a good welfare and for you know, making food, producing electricity, etc. You see that in some of the Western countries, and in particular in the United States, there is, however, good on average availability of water, but also the use of water is quite intensive. So there is still margin for these countries to improve their lifestyle in terms of water use, but the margin is not so extended. You have to look at the northern countries in order to find the regions where we have more margin. Okay, this is the water withdrawal per inhabitant. This is just the withdrawal, and you can see what are the countries that use more water. And this is something expected, and these are the countries where you have the larger use of water, which is also related to availability. But in some countries, for instance, in the Middle East, you see a large use of water that is also fed by groundwater. And in fact, there are some concerns for these countries in terms of sustainability, because when you use groundwater, I already mentioned that the issue is sustainability of water use, because it's you know, the groundwater, we don't really know how much water is there, how much water we can use, and therefore we don't really know if the water use is really sustainable. Let me have a look if there are people in the waiting room. I don't think so. Just 1 second. I want just to check. Okay, good. Perfect. Let's go back to the presentation. Bud is waiting to get into the room. Okay. So this is water withdrawal. This is proportion of total water withdrawal, which is withdrawn for agriculture. This is another good indication because, as I said, the water food energy nexus is extremely important. Keep in mind that most of the water uses, I think I already mentioned this information to you, most of the water use is related to irrigation, to water for food, agriculture. It's at the global level, it takes about 70% of the total human water consumption. And the remaining 30% is split between the industrial use, which is something around 20%, and the water for civil use, drinking water, etc., which is a limited proportion, around 10% of the total amount of water that we use. These percentages are more or less the same that we have in Italy. We have a little bit less for agriculture. It's around 60-65%. And we have about 20% for industry in Italy and about 10-15% for civil use. So this proportion of global water use are those that we experience also in Italy. The important thing to note is this 70% more or less of the total water use that is dedicated to agriculture. This means that when we talk about droughts, the most impacted sector is agriculture. It's also impacted because water for civil use has the priority in almost everywhere. It means that when we experience lack of water, we give priority to water supply for civil use. And therefore, agriculture is the first impacted sector for two reasons. First, it's the larger consumer. Second, it's less priority with respect to civil use. And therefore, again, when we talk about impact of droughts, the most affected sector is agriculture, and you can clearly perceive it, because if you look at the media, for instance, during summer 2022, if you look at the media that dedicated ample space to reporting the drought in the north of Italy, and they focused mainly on agriculture. Actually, during the summer 2022 in Italy, we didn't have water shortages for civil water supply. We experienced shortages for agricultural water supply. And so agriculture is indeed important. And keep in mind that when we talk about agriculture, it's not just agriculture itself, it's food production. And therefore, in terms of socioeconomic impacts, a crisis in the agricultural production is an overall socioeconomic crisis. It's not just limited to one sector. So we have to be concerned, even if, we understand water for civil use is priority, but it's not just enough. If we are given water into the tap, but we are not given water to produce food, this is anyway a huge problem. Okay, now let me talk about, after talking about the spatial distribution of water, let's talk about the temporal distribution. So the purpose of this slide is to shift from spatial distribution to temporal distribution. In fact, if you look at the figure refers to Europe, and you can see the distribution for selected rivers of monthly river flow. Monthly river flow, of course, it's an indicator of water resources availability. And you see that depending on the climate, even in a region, Europe, that is relatively small, relatively, of course, but in terms of distribution of water resources, surface water resources, we have a lot of variability, which is directly related to the variability of climate. When we talk about surface water resources, rivers are a surface water resource. The connection, the relationship, the correspondence with rainfall is very, very close. So the monthly distribution of rainfall is very similar to the monthly distribution of water resources into the rivers, because their time of reaction to rainfall is very short. At most, we can talk about a couple of weeks for the very large rivers, but mostly it's a matter of a few hours. After a rainfall, we see the water into the river after a couple of hours. And therefore, the closeness of rainfall and the river flow is not surprising. Still, in Europe, we have several different climates, and let's highlight some exceptions to what I just said. So I just said river flow is directly related to rainfall. There are some exceptions, and let me mention a couple of exceptions. One is natural. The contribution of snow melt. So in some rivers, we may have abundance of water even when it's not raining, because these rivers take the water from snow melt and glaciers melting. And we may have even floods in those rivers without any rain, because sometimes also snow melt and glacier melting may originate floods. Okay. And we can find this distinguishing feature in the mountain regions, of course, where snowmelt is giving an important contribution. In these regions, if you look at the picture, you may find rivers with the river flow concentrated in summer. This is not because in summer we have precipitation. It's because in summer we have the highest temperatures. And therefore, these are called alpine river flow regime. This is called alpine river flow regime. In most of the cases, we have the so-called continental distribution of river flow in Europe, which means that we have two peaks, one in spring and another one in the fall season. And you can find some examples here. There are some examples of rivers where the distribution is more or less constant. And these are typically the large rivers. They basically receive input from an average of climates, several different climates, and the average is leveling variability. So, for instance, if you think of the Danube gets water from the Alpine region, but also from the flat regions of Germany and Austria, which means that basically the Danube is getting contribution from snowmelt, but also contribution from rainfall, and therefore the variability of the river flow is lower down during the year. Anyway, the seasonal variability, what is called the river flow regime, which is corresponding to the distribution of monthly rainfall, it's another important driver of water scarcity, water resources availability. Just keep in mind that to compensate the uneven spatial distribution, you need to move water. Moving water, it's not easy. I already mentioned that. To compensate the uneven distribution in time of water resources, you need storage, you need dams. Okay. Now, what are the solutions that we may take if we want to adapt to water scarcity? Okay, so let's focus on one risk, which is water scarcity, drought, and let's focus on the solutions. So now for the first time, we are considering one risk and adaptation actions. We are in parallel, I just want to remind you, in parallel, we are estimating risks, which means that for selected hazards, we estimate risk. Why? Because we want to estimate priorities. We want to determine priorities for adapting to climate change. So let's assume now that our priority risk is water scarcity. What are the possible solutions? This may seem to be a trivial question. Actually, it is a frequently debated question. I attended a meeting with the local administrations a couple of days ago, where we discussed the threats affecting this region, the Bologna region, in terms of droughts, water scarcity. There is a difference between the two terms, droughts and water scarcity, which I want to clarify. Water scarcity is something permanent. Drought is something occasional. So we talk about water scarcity when a country is experiencing continuously shortage of water. We are talking of a drought when we face an event that is limited in time in a country where normally we don't have water scarcity. We may experience a season or a sequence of years where we have lack of rainfall. And therefore, it's a kind of temporary water scarcity. So this temporary water scarcity is called a drought. So I was discussing in this meeting about the risk of drought. The Bologna region is not a region affected by water scarcity currently. It is well equipped to withdraw water from several sources. So on average, we have enough water for agriculture, for industry, and for feeding people. But recently we experienced severe droughts. Typically, they are seasonal droughts. They last for one season or for 1 year. And what is relevant here is the summer season. The summer season because it is the season where we need most of the water for agriculture. And therefore, we were discussing this threat. And we discussed in terms of climate predictions and in terms of possible solutions. And this debate is really very live, because first of all, we need to agree with the policymakers and the administrators that drought is a relevant risk. So we have to estimate probability, vulnerability, exposure, and of course, the administrators have several risks to face. They have limited resources. So the first step is to evaluate whether the risk of drought is a relevant risk. In fact, one of my statements was we may also decide to ignore it, because of course we cannot get protected against everything. So we may choose to ignore it. The second step is to decide what is the solution. And so there is a solution, if you look at the slide, that has been traditionally adopted by humans. Historically, when humans needed water, they looked for water supply. And so a solution is to increase water resources availability by increasing the supply. And you may increase the supply by increasing the conveyance of water supply systems, provided you have water somewhere to take. So, for instance, if you have rivers in the mountains where water is available during summer, you can build an aqueduct to bring the water downstream, which means moving water in space, and this can be done for limited extensions, for limited distances. You cannot bring water from the north of Italy to the south of Italy. You would need a water supply system that is too long. The leakage would be too significant, and therefore this is not possible. So one possible solution is to increase the water supply to get water where it's available, but it's not so easy to find places where there is enough water. Typically in this region we have water during the winter in the rivers, but not during summer. And therefore, a second solution is to increase storage. And therefore build dams, artificial reservoirs. But this is a solution that is a bit tough, a bit complicated, because dams are costly. They require a lot of financial resources, and dams have a limited duration because siltation is limiting, is decreasing the storage along the years. It is not easy to remove the silted material. It is not easy because you have the problem of displacing it. You cannot just release mud downstream because there is an environmental impact. And also there is the environmental impact of the structure of the dam, which is, and the lake, which is in any way an artificial infrastructure. But this is a first possible solution: increasing water supply, increasing water storage if it's needed. Okay, and of course, from a technical point of view, there is the question: if we decide to increase water supply, what is the design flow I need? So if I need more water, how much more water? And if we overestimate water needs, then of course the environmental impact is higher and we need more resources. If we underestimate it, of course, the solution is not sufficient. So there is a technical question which is directly related to estimating future water uses, and this is what is most important for us: estimating future climate projections. So in order to decide to make this design, this specific design, but also other designs related to climate, we need projection of the future configuration of the whole system in terms of climate change and in terms of future socioeconomic evolution. So you have to put together these two assessments within an interdisciplinary context. Here you see an interesting figure showing what are the costs of water supply depending on the source. What is interesting here to see is that desalination is still very costly. And there is a range. Of course, you see that the bar are extended in the vertical direction because the cost is distributed along a range depending on the country, depending on the context. And for instance, you see that if you refer to just Phoenix in Arizona, you see that desalination has a range of cost that is very limited because the context is limited. If you go at the global level, there is more variability, but still desalination is definitely more expensive with respect to other solutions. It is expensive also to treat wastewater, and so this is something interesting, because there is a lot of attention nowadays on the reuse of treated wastewater, which is relevant because even if it's costly, keep in mind that we need to treat the wastewater anyway. Before releasing it again into the natural system, we need to treat wastewater. And of course, given that we need to treat it, the opportunity of reusing it, it's an interesting opportunity. Still, it is not very significant yet in terms of volumes, and it's anyway costly and accessible then only in the countries that have the resources for reaching the double target of treating wastewater and reusing it. If you look at surface water, here there is only reference to Southern California, and actually on average the use of surface water is less expensive with respect to the use of groundwater, because groundwater in several cases needs to be pumped. And pumping, of course, takes energy, and the energy has a cost. Here you see a picture that it's not really corresponding to the situation, for instance, of Italy, where groundwater is used, but it is generally more expensive using groundwater than using surface water. Anyway, the cost of water supply is directly related to the solution of increasing water supply. There are other solutions, like, for instance, water demand control and regulation.